Last week we used melting ice as an example of heat transfer. We said that 2 moles of ice warm from negative 10 degrees Celsius to 0 Celsius, then it melts from solid to liquid, and warms to its final temperature, the temperature that meets the temperature of the water cooling from 20 degrees. Energy is transferred from the water to the ice as heat, and the loss of energy cools the water. All of the energy is accounted for, and so it meets the first law of thermodynamics. But what if we run the process in reverse? 2 moles of water molecules transfer energy into the other 10 until they are cooled to 0 degrees. They then continue transferring energy as heat as they freeze into ice cubes, and then the transfer of energy continues until the 2 moles of ice reach negative 10 degrees Celsius. Now, every experience you've ever had tells you that this is not going to happen, and yet, as far as the first law of thermodynamics is concerned, there's no problem. All of the energy exchange is accounted for by both of these scenarios. The first law tells us that energy can be exchanged, and gives us the tools to account for these changes, but it gives us no method or test to judge which direction energy should flow in any one scenario. To look for a rule we can use, let's start by considering a limiting case, one where the direction of change isn't quite so obvious. In fact, let's revisit the simplified system that we've used a lot already, the expansion and contraction of an ideal gas. Let's say that the piston here is free-floating, so that any difference in pressure will cause it to move. If we reduce the pressure on the outside, your experience tells you that the piston will rise spontaneously until the two pressures are again equal. Increasing the pressure will cause the piston to drop until the internal pressure increases enough to match. And in both cases, once the pressures are balanced, then the piston remains still. We've called that irreversible work, mostly to recognize that it's only going to happen one way and does not spontaneously reverse its direction. So what if we take that to the limiting case? If we could make the change in volume so small that the pressures are never actually different, and we could see the piston reverse course spontaneously. That's the balancing case, where there's no spontaneous movement in either direction, and that's where we might look for a function that balances at that point, a function that tells us which way the piston would move spontaneously. For example, if it's greater than 0, then movement is spontaneous, and less than 0, the movement is spontaneous in the opposite direction. And at 0 exactly, then both sides are in equilibrium. We would also expect this function to be a state function, since we don't want it to depend on how the system got to that point. Going back to the melting ice for a moment, we want a function that tells us that ice will melt in water, no matter how the ice and the water got into the glass. Delta U equals NCV delta T, which also equals work plus heat. So, heat equals delta U minus work. The pressure of an ideal gas is defined by pressure equals nRT over V. So work is negative nRT over V dV, and heat is the differential equation NCV dt plus nRT over V dV. To find the reversible heat, or the heat that is produced with an infinitesimally small change in volume and temperature, we need to integrate these two terms. The first one is fine. It's a straightforward function of temperature, so we can integrate to get a function of temperature plus a constant. Even if the heat capacity at a constant volume is temperature dependent, which in reality it is, it's still only a function of temperature, so we're still good. The second term isn't quite so friendly. If we want to integrate over the change in volume, we need to account for the change in temperature that we get by changing the volume. Because remember, in an ideal gas, temperature is volume dependent. But by including the change in temperature inside this term, we end up in a big recursive mess. The easiest fix for this, and the one that we're going to choose, is to divide every term by temperature. That way, we get the reversible heat over temperature is equal to NCV over temperature dt minus nR over V dV. That gives us two differential terms, one in terms of only temperature, one in terms of only volume. And these we can integrate to get NCV ln of T2 over T1 plus nR ln of volume 2 over volume 1. Now we have an equation for the reversible heat per temperature, which is only a function of temperature and volume, themselves state functions, meaning that the reversible heat per temperature is itself a state function. This is the state function we were looking for, one that we'll define as S and call entropy. But what does this entropy function tell us about the direction of spontaneous processes? In order to move away from zero and get spontaneous heat transfer at a given temperature, then we either need to see the temperature rise or the volume expand, or both. Increasing the temperature or volume of a system doesn't necessarily mean that the total energy of the system changes. It just means that that energy is able to distribute over a greater number of states, a greater number of speeds when it comes to temperature, and a greater number of places by increasing the volume. The fact that it's heat and not work is also telling. Remember that the only difference between these forms of transfer of energy is that work is well ordered and heat is random. Entropy is positive for a spontaneous process, and a spontaneous process is one that decreases the total concentration of energy, or one that increases the distribution of energy into a greater number of states. That's why it didn't show up in our discussion of the first law. It doesn't concern how much energy there is, but how it's distributed. This is why we needed a second law of thermodynamics, and that's what we'll talk about in our next video.